All right. Hi, everyone. So we have, just to remind us what we had kind of gotten up to, we did the grand canonical ensemble. Then we derived the occupancy numbers for ideal quantum gases. I said that there were two kinds, fermions and bosons. Fermions we looked at degenerate Fermi gases. And so now we're going to go and look at degenerate Bose gases. So we start off with something called Bose-Einstein condensation. I want to talk about this one first, and then hopefully in the second hour today, we'll move on to blackbody radiation, which is another Bose problem. So we're thinking about massive means mass is not equal to 0 bosons. And just in the same way that we sort of thought about a gas of fermions at low temperature, we're now just thinking of a gas of bosons at low temperature. So they'll also have the same dispersion relationship, that the energy is just going to be p squared over 2m. Yes, standard kinetic energy term for the energies. And we have earlier said that the occupancy, right, for ideal Bose gas is okay. So this is the one that we showed before, and so now what we need to do is think about the physics that can come out of that. So again, we're using the cheat that we used for fermions. The cheat was, rather than going back to the partition function again, we already know the occupancies of all the energy levels. So this makes our life much easier. We can just go straight to the answer. Okay, so things like what is the average number of particles in my sample? So I've got a box, and just think about it this way because it makes your life easier. I've got some box, it's got some bosons in it, and I want to find out, for example, how many particles are in there. So to get the number of particles, I have to integrate this NP. I've got to put in a degeneracy factor G. Give me 1 second and get back to the degeneracy factor. And then I need a density of states, right? So density of states for a three-dimensional box. And remember, this is the formula that you need to remember. Standard one. Okay, where G is 2 times the spin plus 1 is the degeneracy. So if we have a spin 0 particle, then G equals 1. If we have spin equals 1/2, like fermions, then G is equal to 2. If we have spin equals to 1, then G equals 3, and so on. Yeah. So for bosons, S will be equal to 0 or 1 or 2 or any other integer, right? So fermions are half integer, bosons are integer. Okay. So that's what the G is in there for. We had the same thing when we worked out the fermions. G was equal to 2. I just put it in there as this, spin degeneracy. Now we can just go a little bit further and just say G equals 2s plus 1 in general. Okay, that's great. So that gives me I can just make one step maybe to bring out, I can do the integral over space. If I've got some volume V, over 2 pi h bar cubed. I can bring out my factor of g as well, why not? And I'll have an integral of 1 over e to the epsilon minus mu over kt minus 1 d3p. Obviously, I can go further than that, but let's see how we go. So if we push on, we need to then put in the epsilon is equal to p squared over 2m. And that means I need to convert my dp into d epsilon. Let's do that. So d e equals p dp over m is correct. Yep, come back to that in 1 second. So, and then I just want to write p is equal to the square root of 2me. So I get square root 2m epsilon. Okay, question was, actually, I probably don't need that last step, but that's all right. I can stay there anyway. Question was, what is this big N? Big N on the left-hand side here is the total number of particles in my sample. Okay? My total number of particles on average. Remember in the grand canonical ensemble. In the grand canonical ensemble, I have variable numbers of particles. Yes. So this is the total number of particles in some subsystem that is connected to a thermal bath and perhaps a, well, in the grand canonical ensemble also be connected to a particle bath. So you can get more particles, you can get more energy. Yep, grand canonical ensemble. So now let's work out what the density is. The density of particles we usually write as rho. Rho equals g. So it's n. Well, I should write that out just to be super clear that everybody knows what I'm talking about. It's n over v equals. Okay, so I need. Should do conversions? Yeah, why not? Let's just do it all in one go. G m to the power of. If I skip one line, you guys will be fine. You guys can check it yourselves. Square root 2 pi squared h bar cubed integral 0 to infinity of square root epsilon over e to the epsilon minus mu over kt minus 1 d epsilon. All right, so here's our density. Gamma, there's no gamma. Where? Yeah, it's just divided by the volume. Density is number of particles divided by volume. Yeah? Okay, so you get this formula. And now I'm going to start talking about this formula. Because if you look at this formula, this to me looks like hell a little bit. Okay? We've got a little bit of hell space here. The formula doesn't look fun. The constants out the front, we don't worry about too much, but this is some interesting stuff. So take this to the next page and see what we get. Copy. Okay. All right, so we've got this formula for the density. Firstly, there's inside this integral, mu is a free parameter, and temperature. So I've got this this function rho, mu of t. Epsilon is the integrand, so I just integrate over that, right? So that's just a free variable. If if you look at this thing, it may not be immediately obvious what it looks like. So let me draw it for you. Okay. Let me draw it for you on a couple of different conditions. So firstly, Maze, back here. Firstly, this is the integrand as a function of epsilon. Okay, this integrand is a function of epsilon. What does it look like? In the case where mu is positive, it looks like something like this. So I'm going to get rid of the 1 over square root, and let me just draw it like this. This is that with mu greater than 0. Okay, there's clearly an issue here. There's a problem with mu greater than 0. It leads to a pole. Yeah. Now, that means that we have something that is unphysical for mu positive. At the pole here, we have a situation where the contribution of one of the little pieces of energy is effectively infinite to the density. Okay, so we have a divergence in the density for that particular value of mu. Yeah. Another problem is here, you've got some negative density. Does that make sense? Now this needs to be, so this part needs to be multiplied by the square root of epsilon, okay? Because we're in this so it should be only positive. If I do it here positive, okay, I'm still going to get a negative number here, which is not good, right? Okay. What about for mu greater than 0? Sorry, for mu less than 0. So if mu is less than 0, what happens? Then the pole is in the negative space where I don't care about it. So that's okay. So there's a pole down here. Fine. And then up here looks like that somehow. Yeah. So this is the same 1 over e to the epsilon minus mu over kt minus 1. So now in the positive epsilon space, it looks good. And if I now multiply that by the square root of epsilon, I will get something that looks like, what color? Blue. Blue? Blue. I don't like that. Draw it again. Okay. So that's what this thing looks like. And what is the density? It's the integral of this thing. So it's the integral of this thing on here. That's the density. Yeah? Okay. So the problem makes sense only if mu is less than 0. All right? Mathematically, we have some problems if mu is not less than 0. So that's what this graph looks like. There's more to it than that as well. If I take this mu of t, so if I take this rho as a function of mu of t, right, then I can actually adjust, mu and t to make this graph slightly different shape. For example, I might lower the temperature of my sample, but keep the density constant. So take this rho, keep rho constant while lowering T. Now, if you want to do this in Mathematica or something, I recommend it. Or Maple or whatever you like. If you take this temperature and you lower it, you're increasing the rate at which this exponential is getting large. Yeah. So e to the beta epsilon minus mu over kt. So if beta is larger, i.e. lower temperature, if beta is larger, then this denominator here is getting bigger faster. Agreed? Okay, hang on. So if we lower the temperature, we might be going down faster here. Yeah? Lower temperature. Right? One second. I'll come back. And then you might have a graph that looks something like this, where the density has stayed the same, but the temperature has changed. How can I do that? All of these prefactors, G, M, pi, H bar, they're all fixed. So I can't just arbitrarily change the scale here, but I can change mu. So if I make mu get closer to, make mu increases this way, yeah, so if I move that to the right, then I pull in more of this, more of the stuff into the low region. You see that? So if I lower this temperature, right, so make this go down faster, but at the same time I bring this guy over into here somewhere, so that this exponential is actually coming back in here, then I can get a shape that looks like this and keep rho the same. So if I low t and keep rho constant, I can do this by increasing mu towards 0, i.e. absolute value of mu goes down. Okay. Yes, you had a question. Yeah, so if I take this, just this part here, fair enough. The question is, the graph doesn't look quite right when I multiply by root epsilon. Probably doesn't, but you've got this guy here, some decay, exponential decay, right? From this part. And I multiply it by square root of epsilon, which is just that. So I'm going to get something that looks like this. Yeah. Okay, so if I keep the density constant, now why would I want to keep the density constant? Okay, but that's a physical thing. I've got a number of particles in a box and I'm lowering the temperature. So as I lower the temperature, the mu has to increase to keep all of the statistical physics correct. Statistical physics we already know is correct. All right, it's based on very simple principles. So what does that look like? It looks like this. I plot mu as a function of temperature. I start off at some point where mu is negative and t is negative, right? Less than 0. Sorry, t is positive, mu is negative. And as I lower the temperature, right, I have to increase mu to compensate until some point here, it's going to hit 0. Now, that you're going to have to prove to yourself. How? You're going to have to grab out Mathematica or whatever. So the graph looks something like this. So this is keeping constant. Okay. So we have the introduction of a critical point. At some temperature Tc, the chemical potential vanishes. Below this Tc, this critical temperature, we can't keep the density constant anymore. Can't keep the density fixed. So Tc is a special point. Of Bose-Einstein condensation, below which we cannot keep rho constant. Okay, so something funky is going on there. All right. What is this TC? I don't need that bracket anymore because mu equals 0. So epsilon minus mu, mu is equal to 0. Oh my gosh. So used to writing it. Epsilon over KT minus 1. Okay. D epsilon. Little transformation. Set x equals epsilon over KT. We set x equals epsilon over KT. Then we have to take out a little factor. So we get, so someone last week asked me, what integrals do we need to have? Oh no, and I said, you don't need to know integrals. What you would need to do is something like this, where you transform it, from a thing with like extra factors to a standard integral which has no like special factors in it. So square root x over e to the x minus 1 dx. Okay, so there's no like free parameters in that, right? So I used, this is just some arbitrary let x equals epsilon over ktc. All right, fine. So do this integral, and then this integral has a value, a numerical value, okay? The value, you do it numerically, you get 2.315, some approximately equal to 2.315, okay? Some number. Okay, and so then you take this thing, and then you get, therefore, KTC is equal to all this stuff, root 2 pi squared 2.315 g, all that to the 2/3. I've got h bar squared over m. I've got density to the power of 2/3. Okay, and what's all that? That's approximately equal to, turns out, 3.31. Okay, 3.31. Just numbers. G to the power of 2/3. And then h bar squared over m. It's good. Density to the power of 2/3. Okay. So it gives you a critical temperature as a function of the density, as a function of standard constants. So you have a point at which degeneracy has come in, and we can no longer like ignore it. At this point, we can't keep our density constant. The fact that these things are bosons really matters. So what's going on here is that we have again reached some kind of degeneracy temperature. If you go back and you look at the first degeneracy temperature that we pulled out, it had the same basic structure as this one does. So this part here, once again, right? I said this was again going back, we had like comparing the Compton wavelength to the spacing between the particles, and we got to this with some factor out the front. Then we did it again for fermions, and we got this with some different factor out the front. Now we've got some new factor out the front, but the same basic size. Yeah. So once again, we find the same degeneracy temperature. Okay, so that's Bose-Einstein condensation. Let's figure out what we're actually looking at here. What happens below this temperature? So something funky is going on below that temperature. My mathematics is now breaking. What am I going to do about my mathematics breaking? it comes down to something quite subtle and not at all obvious. So let me go back and just show you what's happening. Below that temperature, something funky is going on where I've got this energy equals P squared over 2m, and that's giving me this integral over energy here from 0 to infinity. Yeah, but it's quantum mechanics. In quantum mechanics, it's not that there are infinite number of energy levels. They're discretized. And so what's happening here is that they're all going into the ground state, but my mathematics here doesn't allow them all to go to the ground states, because I've said that there's this density of states d cubed x d cubed p over 2 pi h bar cubed. And that does not let particles go into the ground state because I get this square root x epsilon at the top here, right? So the ground state, because it has, at normal temperatures, the ground state has no particular interest. It's like maybe there's a particle in there. Who cares? A particle out of 10 to the 20 particles or 10 to the 10 particles. Doesn't matter. Now it matters. Now it matters. And it's because it matters that this has broken my mathematics. Yeah. So I've made an approximation here. I've made the approximation here. And now I need to pay for my approximations. So let's see how we go. What I'm going to do is standard methods. Below TC, we need to account for the ground state separately. So, right, and I talk about that a lot in the thing if you want to think about it. So basically what we're doing, we've got some density of states n, which is the average occupancy that we worked out before. And we've got some epsilon E. And so I've got like a bunch of, let me draw it with purple. Make it a bit fat so you can see it. So we've got a density of states that looks something like this. It's discretized. And the ground state here is the important one. And this small gap here between the ground state and the first excited state is small. But at some temperature, this gap becomes critical to us. So basically what I've done is I've replaced this like set of states by an integral, and the integral killed off the ground state effectively. It killed off this ground state because I said square root epsilon. Okay, let's put him back in, save it. So remove it from the sum and we put it back in separately, and we can write something like this. Is equal to, first state is the ground state, epsilon equals 0. Plus all the other states. Yeah? So taking out the first state separately. And then what I can do is I can say, okay, that's cool. We can write n bar is equal to first state here plus the second state. That's the one I've already worked out. It's a volume gm to the 3 on 2 over root 2 pi squared h bar cubed. Same integral we had before. Okay. So this is exactly the same thing, but now I've just done a slight twist on it. I've pulled out the ground state. I'm doing that one separately. So this is the number of particles here, with epsilon equal to 0. And this is the number of particles with epsilon greater than 0. Okay, so just separate those two out. So these are the number of particles that are in condensate, we say, in condensate. So they're all going into the same state. And the ones greater than 0, they're the ones that are above condensate. Above condensate. Okay. So below the condensate, or in the condensate and above it. Bosons are different to fermions. The big difference is that bosons can have multiple particles in the same state. When I go to low enough temperature, lots of the particles can enter that same state. Yeah, they can all go into the ground state at low enough temperature. That is a completely different physical process to what would happen with fermions. Fermions are going to have to fill up all of the available states one at a time because that's all they can do. The bosons, they don't mind hanging out together. So they all fill out into the ground state. Different story entirely. Okay. So this is the way that you solve our little problem. We've pulled out this ground state separately. Remember, at any physical, like a big temperature, what happens? At a big temperature, the number that are here, whatever it is irrelevant to statistical physics because we're talking about big numbers of particles. And if there's 1 or 0 in the ground state or 20 in the ground state, it doesn't matter. Yeah. But at low temperatures, it's critical because they're all hanging out there. Yeah. Suddenly everyone's gone into the ground state. So we need to account for it separately. Okay. How many particles are not in the ground state? And then we'll work out the number that are by subtraction. Absolutely we can. No, we can definitely know exactly where they are. Yeah, statistical physics. Absolutely. Where are they? The number of particles with epsilon greater than 0 is V gm to the 3/2 over √2 pi squared h bar cubed kt to the power of 3/2 integral 0 to infinity. I've written in terms of x here again. That's okay. Okay. Where are they? These are the ones that are in the ground state. These are the ones that are not in the ground state. Your question is, whereabouts are they? The answer is, this is the formalism, that this is the probabilities function for those energies. This is the filling of those energy levels. So how many particles are at the energy equals, I don't know, 50 electron volts. I put 50 electron volts here into the energies, right? For my particular value of mu. And I say, well, at 50 electron volts, at mu equals 0, for example, this thing here is easy to work out. Yeah, that's the number of particles at that energy. So I know exactly where all of them are. All of my particles are given by this formula, except for the ground state, which is given by this formula. So we work out how many are not in the ground state by just doing the same thing, set mu equals 0. And that is some function. That's a number, the integral. There's some numbers out the front. That number is going to be proportional to n, and it's t over tc, just because the units have to look like this, to the power of 3/2. Okay. TC we already worked out before. This is the same TC, exactly the same. So this gives me some function of the total number as a function of t. So the number of particles in the condensate in the ground state is just that. In other words, I'm getting the proportion of number of particles which are in a particular state. What does that look like? So it looks like this. I've got N naught versus T. There's some critical temperature TC. Above the critical temperature, the number that are in the ground state is close enough to zero that I don't need to worry about it. Yeah, there might be a couple in there. I'm not saying it's 0, 0, but it's close enough to zero that relative to the rest of them, it doesn't matter. And below that temperature, below TC, right, it goes as 1 minus T to the 3/2. That just looks like this. It goes up to big N. Yes, your question.
So when you said just substituted in, what did you run in critical?
This one?
Yeah.
That's just numeric. That's 3, whatever I said it was, 2.315 is this integral. Of? Right, so for a particular value, so you want to know what the density, you want to know what the distribution is at some particular temperature. Right, so you have to look at the energy. So remember how we do this, how we go from integrals to discrete values, yeah? The number that would be at this energy level is the number between at epsilon equal to something, d epsilon. Yeah. So number at epsilon equals 50 electron volts d epsilon, right? In some little gap. Yeah, because they're quite closely spaced, these energy levels. Very, very closely spaced. So I say the number that are at 50 electron volts in that little regime, d epsilon, is given by this number. Yeah. That will give me all of them. So that's just the sum over all of them. If I want to know how much are here, like how many are between 50 and 100, I would go integrate between 50 and 100. Yeah. If I want to know how many are at the second energy level, it might be between 0.2 electron volts and 0.4 electron volts or whatever it is. Yeah. Yes. Yeah. So the question was for those at home, this stuff is a probability density function. Yes. Sort of, except for the fact that this is giving me an actual count. But yes. Oh yeah, but you need to just be careful because it's not normalized to 1. If you normalize this thing to 1, then yes. With this guy as well. But yeah, sure. If you normalize it all correctly, then sure. Otherwise, it's a count. So what this has shown me is that below some critical temperature, right, I get this this occupancy in just the ground state N naught. So this is occupancy of ground state. And if I'm at 0 temperature, all of the particles are in the ground state. Yeah. But if I'm like below TC, they're already starting to fill up that ground state significantly. Yeah.
So for the integral, we said that it can't have a value of the ground state because basically multiplied by 0.
Yeah. Basically correct. Yeah. Basically multiplying by 0. Mm-hmm.
Yeah.
Mm-hmm.
For at least fermions, there was like an epsilon 0 that was non-zero.
Yes. In fermions, just to be clear, we had I just drew it up with like a series of marks saying these are my states, E0, E1, E2, E3, E4. And then we put in the dispersion, E equals P squared over 2M. So now my E0 is close to 0. P squared over 2M is close to 0, right? If I'm going to do this properly, I'm going to have to put it in a box and do the quantum mechanics for the ground state, right? But it's going to be really close to 0, be like half H bar omega, or like, do you know what I mean? Like that kind of really, really tiny. Yeah. Yeah. And in the case of fermions, it doesn't matter because I can only have 1 or 2 particles in the ground state anyway. So I don't care. Yeah, whether I include it or not is irrelevant to my life because there's only 1 particle per state. In this case, right. It's close enough to 0. I mean, like close enough. No, it will not be if you do quantum mechanically, you got a particle in a box. You do the Schrodinger equation, you get some energy. Yeah, energy is not 0, right? It's very, very close to 0 because it goes as 1 over the volume. So it's really, really small. Yes, really small energy, but it's still not 0, not exactly 0. Yeah. But it's relevant. Yeah, exactly. It's relevant because that ground state is now kind of special. They're all hanging out there. Yeah. So usually I don't care about a single state. I only care about your density of states. I only care about, oh, I've got this in this part. And then the number of states which are at 0 is like maybe 1. Like the density is really low. It doesn't matter. I do the integral from 0 to infinity, so it doesn't matter. But then in the case of bosons, when they're all hanging out there, now I have to worry about a particular state, the ground state. Yep. So this thing here is n0 over n, which is the 1 minus t cubed. That is the order parameter. I don't know why I'm telling you that, because these are the kinds of things that I can't remember. So that's the order parameter. Yeah. Mm.
It's not necessarily 0.
Yeah. Yeah. Yeah, correct. So above here, there might be particles in the ground state. Yeah. The number of particles in the ground state will be given by the usual formula. The density of states is small. There'll be particles in there. I don't care about them because I've got a lot of particles. Yeah. Remember, this is statistical mechanics. Lots of particles. Yeah. And what's interesting here is when you have lots and lots of particles, you don't worry about one level, except for Bose-Einstein condensates, where one level makes all the difference because they're all hanging out there. That's a Bose-Einstein condensate. Okay, is 12:48. I think this is a good time to take a little break, and then we will come back at 1 p.m. So no, not quite 1, maybe a bit before. Let's give ourselves a little bit of time. Maybe just, yeah, like 5 to 1, or like take a 5-minute break, maybe 10 minutes at most. And we'll come back and we'll do black body radiation. Okay, and that one takes a little bit of time as well. So probably want to get into that. Yeah, like 5 minutes time. So I'll pause the recording. Oh.